Hey everybody, welcome back. Today we are continuing to build on the foundation that support our energy savings efforts in the SEM program. This is a three-part series that all support workshop number 3. So just to zoom out for a little bit and remember the content of this specific model, I wanna think about the objectives of this workshop. The first one is learning different approaches to track energy performance. The next one is learning how to analyze and understand energy performance results. Now, we've done 2 other modules up to this point. We looked at an introduction to energy tracking and KPIs. We talked about methods of energy tracking. And then here in this module, we're really going to do a deep dive into energy intensity models. So just as a general reminder, the overview and general process that we use to build a model is as follows. First, we collect data. Then we work to understand relationships. Then we define energy drivers. And finally, we work on building the model. Now I'm going to pass it over to Kevin, and he's going to dive into more detail on how a model is created based on a hypothetical case study.
Thanks, Nick. So let's go ahead and let's assume a company, Gizmic Gadget Company, came to us and asked us to build them an energy model. Well, one of the first questions we need to sort out is what are the potential energy drivers? Now, in the case of Gizmic Gadget Co., let's just assume that they're a manufacturer that produces several final products based on one single raw product. They typically operate 24 hours a day, 5 days a week, but it can vary. And Gizmo Gadget Company, they gave us a couple of years of historical energy and production data. So what we need to figure out is which energy drivers should we use in the energy model? That is, what independent data streams like production and weather and operating schedule are the most capable of predicting energy use for a given day. So for the case of Gizmo Gadget Company, let's assume that they gave us the raw product that they go through in any given day, measured in pounds, the amount of finished product A that they made for a given day, measured in pounds, their operating schedule, and the daily average temperature for the nearby area. So one of the first things we want to do is try and figure out what impact do these potential energy drivers have on energy use. And now that we've kind of collected some of the data, the next step in the process here is going to be to understand relationships. Now, to do that, one of the first things we like to do is to just chart the data. And what we're looking at here, we call this a scatter plot. So I'll turn on my laser pointer. And what we've got is on the horizontal axis, we have that raw product data they provided to us measured in pounds. It goes from 0 all the way up to 8,000 pounds. On the vertical axis, we have energy consumption. This is measured in kilowatt hours a day, and it goes from 0 to 40,000 kilowatt hours a day. Now we have all these blue diamonds throughout. Each one of those blue diamonds represents a single day. And in this case, we have 365 of them on the chart because we're representing a 1-year period from before Gizmo Gadget Company would have joined the SEM program. We might call that their baseline period. Now, one of the initial observations we might make about this data set is that most of their energy using days are above about 25,000 kilowatt hours a day. And that's kind of all the data points above this line. They also do have some that are lower than that. They've got this clump down here where they're not going through any raw product. And they have this clump where they're kind of going through some raw product, but it's not quite that much. So as I look through this, one of the first things that jumps out to me is we have this very nice linear relationship up near kind of the upper right end of this chart. And what that tells me is as Gizmo Gadget Company goes through more raw product on a given day, there is a predictable increase in their energy consumption for that given day. What that tells me is that this is likely a good energy driver. And all I mean by that is a change in the amount of raw product they go through in a single day is likely going to be able to relatively accurately predict an increase in energy consumption for that day. Now, what's important to point out here is there's more going on than just that, because on a single day, when they, let's say, went through 7,000 pounds of product, they could have used as low as 30,000 kilowatt hours a day or as many as 37,000 kilowatt hours a day. So it's not that raw product is the only energy driver, but it's one of the ones we should consider. So let's go ahead and let's look at some other potential energy drivers. Now we're looking at, it's the same company, it's still Gizmo Gadget Company. And on the vertical axis, we have energy consumption measured in kilowatt hours per day. But on the horizontal axis, we have something different. Now we have that finished product metric. It's finished product of product A in pounds per day. This one goes from 0 to 2,500. Now, this data set looks quite a bit different, right? Still, we have each one of these blue diamonds is a single day. There's 365 in the chart. But now we see there's a whole lot of days where they're not making product A. Maybe they have product A, product B, product C, product D, all sorts of them. And on days when they are producing product A, the relationship is much flatter. So this green line represents kind of the average expected energy use as the amount of product A changes. And that thing is just about as flat as they come. Now, what that tells me is that a change in the amount of finished product A that's manufactured at this facility does not result in an expected change in their average daily energy use. That tells me it's not a good energy driver. A good energy driver would allow us to predict a change in energy use based on the change of some other independent variable. And because it says that nice flat relationship, it's not a good energy driver. Let's look at another potential energy driver. So in this case, this is still Gizmo Gadget Company. We're still looking at energy consumption per day on the vertical axis. But now we're not looking at that scatter plot. Now this is a little bit different way to view the data. This is actually a time series plot. The horizontal axis is time going from January 1st all the way to the end of February. And what we kind of see is this particular facility, this is their actual energy use from their electric meter just over time. And it has this very typical kind of sawtooth pattern. We see this for a lot of manufacturers where it's high for a number of days and then it drops down low, and it's high for a number of days and it drops down low. And what's especially interesting here is if we look at how does this pattern line up with days of the week, something really just jumps out at us. So each one of these low days happens to be a Sunday. And what that must tell us is, oh, this facility must not have much going on a Sunday. Maybe there's no production. They schedule off a whole bunch of equipment. No one's in the office buildings. And therefore, Sunday is likely a pretty strong predictor of energy use. Therefore, it's a good energy driver. In this case, on Sunday, the average energy use is only about maybe 10,000 kilowatt hours, whereas on other days of the week, it averages closer to 30,000. So a Sunday results in 20,000 kilowatt hours lower energy use than any other day. So in this case, a Sunday energy driver, really it's just an indicator variable to let us know which days are Sundays, would likely be a good energy driver. And lastly, let's look at one other type of data here. So in this case, we've got energy consumption measured in kilowatt hours per day on the vertical axis. We're back to that scatter plot type of diagram. But now we have ambient temperature. It's just the outside air temperature measured in degrees Fahrenheit, going from 0 all the way up to 90. Now, what's interesting with this one is it's not so much a linear relationship. We do have linear periods, right? Up in the upper end of the spectrum, we're above about 40 degrees. We have this nice steep slope. So as outside air temperature increases, energy use goes up. Maybe they've got a large chiller plant or a large cooling load. So as it gets warm out, those systems have to work harder. However, once we get below 40 degrees, that relationship changes. We can't just extend this green line because the data has a different form, and it actually flattens out quite a bit like this. And we might draw an invisible line down the middle at about 38 degrees, and we would call that point our change point. Now, whenever we are looking at energy drivers, we want to make sure that we are creating a relationship that most accurately describes the actual data set. So when we look at building an energy driver, in this case around ambient temperature, we want one that accounts for that change point. We want one that will kind of follow these green lines and have a really shallow slope at the lower temperatures and then get steeper. We would not want to just put a single straight line across there, because then our single straight line would be pretty far off at around that change point, and we would introduce more error into our model. And this kind of understanding really only happens when you chart the data and you explore the data to look at different types of fit and to see what results in a model with the lowest fit and the best fit and the lowest error. And that's the kind of stuff that the SEM engineers are going to be doing when you provide them with your energy driver and your actual energy use data, is they'll be charting all of this to see what is the proper relationship for your facility between outside air temperature and energy use and different production metrics and energy use and different operating schedule variables and energy use. So for the case of Gizmic Gadget Company, just to kind of summarize what we've just done here. So we looked at a number of different energy drivers, and what we ended up finding was raw product measured in pounds was a good energy driver, right? What it had is it had this nice linear relationship, especially when we were in the higher energy use ranges and when they had, notable production going on. Raw product measured in pounds was a strong energy driver. We also looked at the finished product metric. In this case, it was daily product A measured in pounds. And this is the one where even though they would produce quite a bit more daily product A, as that amount increased, the relationship with actual energies was completely flat. So an increase in the daily product A metric did not result in any appreciable increase or decrease in actual energies. In that sense, it would not be a good energy driver. We also looked at the operating schedule, and we said that for every single Sunday, this facility uses about 20,000 kilowatt hours less than compared to other days of the week, so that is likely a very strong energy driver. And lastly, we looked at the daily average temperature. And again, we kind of noticed there that it's not always just that straight line, right? We can't always just draw a totally linear relationship between the energy driver of interest and actual energies. Sometimes we have to break it up by looking at things with a change point or a non-linear relationship. So at this point, our next step really is just to take these energy drivers and build our energy model. And the heart of an energy model is just this equation that allows us to predict energy use. And what we can kind of see in here is we're going to have a term that accounts for each one of our data streams that was provided that we decided was a good energy driver. So we decided that weather factor was a good energy driver. It might have a change point in there, but we want that to be included in our equation to predict energy use. We also said that the weekend influence was important to consider, and so was the amount of raw product that the facility went through. Now, the last item that's also in here is this constant. And all the constant is, it's a term that doesn't change. It's a static factor. And what it accounts for is when all of these other variables that do change based on the condition of the energy driver, when they're all neutral. So when there's not really a heating or a cooling load, and there's no weekend influence, and there's no raw product being processed, well, the facility is still going to use some amount of energy. And that's what we pick up with the constant. So that's also could be called the base load of your facility. So by taking into account that base load of that constant and all the other significant energy drivers, we can now pretty accurately predict energy use based on a kind of wide variety of conditions. So let's go ahead and let's look at that a little bit different way for Acme Manufacturing. Sorry, for Gizmic Gadget Co. So in the case of Gizmic Gadget Co., we have their actual energy use. And this is the same data set we were looking at before. Previously, we had it in the scatter plots where we had all the different diamonds that represented a day. Now we're just showing you it as a time series. So in this case, now we're going from beginning of January all the way to the end of the year. We have energy consumption measured in kilowatt hours per day from 0 to 40,000. And this is just directly what the data from their electric meter looks like. Note they have all of these low points in there. That's all of those Sundays, right? And this actual energy use is also going to kind of inherently account for changes in production and weather and all the things that impact energy use of the facility. What we can do is we can layer on the model's prediction as well. And we talked about how the predicted energy use is really just this formula shown down below. It has the constant, a weather factor, the weekend influence, and raw product all taken into account. We're going to kind of fit that model prediction based on the actual energy use during this period of time. And this period of time is really important to focus in on. This data set is all based on, typically it's a 1 year period from before Gizmet Gadget Company joined the SEM program. And that's really important because what that does is that means that your daily prediction reflects the energy signature of the facility from before they joined the SEM program. And that's really important because as we run that thing forward, as you get into the SEM program, now we have a point of comparison to how the facility performed before the site joined the SEM program. We compare it to their actuals once they're in the program, they're saving energy, and that difference will be our savings. So the only other thing that's important to call out here, again, we're looking at the baseline period. One of the other things your SEM engineer is going to be looking at is the fit between the predicted energy use and the actual energy use. And ideally, we want a really nice, tight, close fit, which we see for the most part throughout this. We see the kind of yellow and the blue series lining up really nicely. There is a period over here where the actual energy use is a bit further off from the predicted. And what you might find is if you send this data over to your SEM engineer and your SEM coach, and they start running these trials to build your energy model, they might reach out to you with questions and say, hey, it looks like, there's this 2 week period in July where actual energy use was way above the models predicted. What was going on then? And you might have to dig into a little bit, and hopefully you can find that, oh, that's when our variable frequency chiller was offline and we had to run the old dinosaur chiller that's super inefficient. So that impacted the energy signature of our facility. And then we can kind of take that into account in building your energy model and understand why the model didn't do so well during this period of time. All right, so now that we have the model built and we have this way to predict energy use, we want to start thinking about how we're going to analyze results. And we're going to start off by looking at a pretty simple schematic here before we jump back into the data for Gizmet Gadget Co. So in this case, we've got our predicted energy use up top. That's going to take into account all the different energy drivers that are relevant for the facility. The vertical axis here is energy use in kilowatt hours. The horizontal axis is going to be time. And let's just say around here, this is when first year SEM began. Now, what we're going to do is we're going to collect actual energy use. And prior to the start of first year SEM, we expect that actual energy use and the predicted energy use to line up really nicely. But then what we expect to see is once the first year SEM program starts, and it might not happen right away, but once you start actually doing some energy projects, what we would expect to see is we expect the actual energy use start to drop lower than the model's prediction. And the difference between the two will be your savings. And the reason that happens is the predicted energy use, that's going to reflect the energy use that would have been expected had you not joined the SEM program. That's why that stays kind of consistent and up high. But again, once you get into the SEM program and you start completing projects, we expect actual energy use to go down. Now, in this simple schematic, it's pretty easy to see that actual energy use is below predicted, so there's savings there. But in the case of most facilities going through the SEM program, there's a lot more noise in these two data sets, and it's a lot harder just to instantly see if actual energy use is below predicted. So we layer on this extra series here. We call this our energy savings line or our Q-sum line. And what that's going to do is it's going to give us a nice visual way to see how the savings stack up over time. So let's just say for this particular fictitious company, let's say on the very first day of SEM, they reduce the pressure in one of their key energy systems. And that is what starts to drive actual energy use lower and starts to get us savings. Shortly thereafter, they improve their startup procedure. Then they tune their VFD settings. And finally, there's some compressed air leaks before they go on and do even more. Now, what I just want to point out here is you'll notice at the beginning of the series, before first year SEM started, that Q-sum line was very flat. And as this particular customer started to do energy projects and the actual energy started to get lower, this Q sum line also starts to drop. And the slope of that line becomes steeper and steeper as the difference between the predicted and the actual becomes wider and wider. That's how these Q sum lines work. So down is good, and the slope going down indicates the savings rate. And the steeper that line is going down, the higher the savings rate. So with that, let's flip back over to Gizmo Gadget Co. Now we are looking back at the baseline period. We've got a really nice fit between actual and predicted energy use throughout almost the entire baseline period. There's a couple little spots where, yeah, it doesn't fit too well, but it's good enough. And that's going to be the case for many of these energy models. There might be a couple little periods where it doesn't fit exactly, but we have ways to tell if the fit is good enough to be able to get used for an SEM program. Now let's say we zoom forward. Now what I've done is I've scrunched that baseline period up into the left-hand portion of this chart. It's shown with the gray shading. And now we're going to assume Gizmo Gadget Co. starts first year SEM right here. And we have about a year of them in the SEM program. Now what we don't have here is we don't have that CUSA line. And we're going to zoom way, way into a single week period while they're in the program to see how that QSUM or the energy savings line gets built. So that's what we've done here. We're now zoomed way into a single week during the SEM engagement. So we're looking at the week of April 18th. And what we've got this light blue series. That's their actual energy use for that given week. We also have this yellow series. That's the model's prediction, right? So this is going to account for the amount of raw product that they processed. It's going to account for the outside air temperature and the operating schedule. And then down below, we have this gray shaded period. Now, all that this is the difference between the actual and the predicted. So we can see is on this first day, the predicted was a bit higher than the actual, right? They were saving energy. And that's why this is below the zero line. This reflects the daily savings amount. On this next day, the actual was higher than the predicted. So this is above the zero line. In this case, this represents poor energy performance, which we often call backsliding. They then go into a several day period where the two are very close. Now, actual is generally below predicted. So we see a very narrow band for daily savings until the end of this series when they have this huge drop in actual. So they've got a very large daily savings rate. So all that's being communicated here is just kind of daily savings over the course of the week. Let's see how that plays out with a QSUM line. So I've now added the QSUM line onto that. And let's go ahead and let's look at how this all pans out. So at the very beginning, the QSUM's going down because they had this nice little bit of savings where actual below predicted. However, the next day, they backslide a little bit and the QSUM actually goes up, right? We follow that with 5 or so days of very modest savings, and we have this long, very slow, very flat, but downward QSUM slope. Again, that signifies we're on a savings slope, but it's a very low savings rate. And then at the very end of this, we have a very big difference between actual and predicted, where actual is way below predicted. They have a very high savings rate for a single day, so the slope of the QSUM gets much, much steeper. Okay, let's zoom way back out again. And let's think about this for Gizmo Gadget Co. on the bigger picture level. So now we have this little gray shaded period. That's the very tail end of their baseline. We're going to mostly look at their performance while they're in the SEM program. So again, they started their SEM program right here. Let's layer on the actual and predicted energy use. So now we have actual energy use in light blue. We have the model's prediction in kind of yellow. And now what's interesting is this data series, this is while they're in the SEM program. And now you can kind of see what I was talking about before, where it's oftentimes hard to tell once they're in a program. If you just have actual and predicted, are they saving energy? I look at this chart and I can't clearly tell if actual is consistently below predicted. There's just so much noise going on that it's hard to kind of pick it out. And this really drives home the value of having that QSUM line. So let's go ahead and let's layer on that QSUM line, often called the energy savings line. It's going to be shown here in green. Now, they start off with that going up just a little bit. And what we said before was down is good. If down is good, that means up must not be as good. We call that a backslide. And so they start off with a little bit of a backslide, right? They're using a little bit more than that model predicted. However, as they get a couple of months into the program, maybe they hold their treasure hunt, they find some of those juicy gems, they get them done, and their actual energy use starts to drop, even though it's hard to see just up above here. But when we layer on the Q sum, it really starts to reveal those longer term trends, and they get on a saving slope. That saving slope gets a little bit steeper as they do more projects, and they maintain that throughout the bulk of their program. So this Q-sum line really is a key visual way to understand energy performance trends over longer periods of time. What we've shown you here is a Q-sum mock-up for a fictitious company, the Gizmic Gadget Co., as an Excel-based tool. That's not quite going to be how you're going to see it while you're in the SEM program. In the SEM program, we use the energy performance platform, and your view of it will look something more like this. Now, it's the same data set. You have similar kind of controllability and views. The color is just a little bit different. So in this case, we've got the blue series hiding back there. That's the actual energy use. It's very challenging to see, but there is the model's prediction shown there as well. The one I really want to call out though is that pink series. That's going to be that energy savings line or that Q-sum line. So in this case, for this particular customer, they started off, relatively flat and they got on a very slight savings slope, then followed by a little bit of backsliding, and then they really got some projects done. And we saw that Q-sum take a nosedive and really indicate strong savings that persisted throughout the rest of the SEM engagement. And this is going to be a key kind of communication tool and a way to check in on energy performance while you're in the SEM program. Now, I do want to highlight a couple of key dates if you're using an energy intensity model to quantify savings while you're in the program. So typically the first 8 or so months, 8, 9 months of the SEM program, we call the implementation period. And all we mean by that is it's the period of time when you should be kind of establishing SEM practices, like holding energy team meetings, building out your team, drafting commitment statements, all the good stuff that helps support good energy management, and working on implementing those energy projects and monitoring results. We want to make sure we get some of those bigger projects done early so they're in effect by the time we get to the reporting period. Because the reporting period is the time that we use to establish your annual energy savings for your first year SEM program. In this case, we show that as the last 3 months of the program. So for those who are starting first year SEM, your program likely began October 1st. And so we have until, let's see, the end of June or so would be a standard implementation period. And then the reporting period would be July, August, and September. And again, we want to get some of those biggest projects done before the reporting period starts. So they're kind of baked into your data throughout the entire reporting period so you get full credit for them. I do want to highlight that not every not every site's going to have a 3 month reporting period. They may change. So we may have a number of organizations who have a 6 month reporting period. You can work with your SEM coach and SEM engineer to figure out what your particular reporting period is. Those get adjusted depending on your energy use profile. So if you have a very seasonal energy use profile, you might have a longer reporting period. The other thing I just want to call out is the implementation period. We don't want you to stop establishing SEM practices or doing energy projects just because you're out of your implementation period. So I like to put this little blue line on there because in reality, even if you get a project done at the very end of the reporting period, you may not get full credit for it in this SEM program, but it would just roll right over to the next year. So if you stay in the program, you would get credit for that project next year. So yeah, there's always a way to kind of pick those up. So with that, we've gone through a good bit of detail of how the energy model is built, how to interpret the results, and now I want to pass it over to Nick to talk about making a connection from the energy intensity model to the energy projects that you all be working on completing.
Thanks, Kevin. I always love talking about the energy models and just geeking out about how they come together. Never get tired of it. So now we're going to connect how projects really connect with savings trends in the energy model. So, at this point, you're probably familiar with the Energy Performance Platform, or EPP, and the Energy Projects tab, which is where all the energy projects and energy management activities are tracked. You may hear us refer to this as your project list, which is the name we use in SEM to refer to the tool used to manage all SEM projects and activities. Now, it's important to keep your project list up to date with project notes, including when projects are completed, so we can help define a narrative behind why your energy performance is changing over time. Now, let's jump back to the Gizmo gadget example here to connect some of these dots. So if we revisit the QSUM model and layer on opportunities on top, we can clearly see how our changes impact facility performance. So in this slide, you can see that there are event tags here for each of the projects that were completed. Now, it's not that dramatic, but what you notice is each one of these projects is completed. There's a slight change in trend of the model slope. Now, this here is really kind of how we connect the impact of the projects to the energy performance at your site. Now, one great feature of the EPP is that it will add tags to your model's performance chart as you update each of your completed projects or mark a project complete. So each of these project examples requires coordination and likely training with your employees. In order for them to turn into real savings, you really have to make sure that they persist. Well, we want to thank you all for tuning in. We really hope that we have provided a solid foundation for understanding energy intensity models. This is initial training on models, but we will continue to work with your team to explain how models are developed and tracked. As you work through your own model, troubleshoot issues, analyze trends, and share out your performance, you'll continue to grow on your expertise working with the energy intensity models. Now, this is the final video in our three-part series as part of workshop number 3. We want to thank you for taking the time to learn more about tracking energy performance that will ultimately support your energy savings efforts. And as a quick reminder, there's a simple quiz and a short evaluation, and the completion of those enters you into a raffle to win some prizes. Thank you all for tuning in for workshop 3.